of this summer school. Today's topic is the Simon-Leap inequality and the infinite volume limit. And before going ahead, let me give you a very brief motivation to see where we're heading. As will be explained tomorrow, we can, well, it is possible to control the two-point function for the weakly self-avoiding walk in 4 dimensions using a renormalization group method. But that method relies on a finite volume approximation and works in the subcritical regime. And one of the results of today's exercises is that that this is good enough that we can take the infinite volume limit in the following sense, that we look at the two-point function on the torus and take its volume to infinity, and then the parameter up to its critical point. I'm going to recall what the weakly self-avoiding walk is. It has been introduced in the first lecture, but I'm going to be using slightly different notation, which is also more compatible to the notation that will be used tomorrow, if I'm not mistaken. And we're going to be looking at the discrete time weakly self-avoiding walk today, though tomorrow will be mainly about the continuous time weakly self-avoiding walk. So we are starting with some graph, which I call gamma. And for today, this will be either the hypercubic lattice ZD or a discrete torus of length L. So this will be. So gamma will be. These are the 2 examples we have in mind. And I'll also write TDL. And let me denote by EX the expectation of a simple random walk, XN. This is a simple random walk on gamma, started at X. And by I sub mn, I will denote the number of intersections a walk does between times m and n. So this is the sum from m less than I less than j n. So this. So this is the basic notation we need. And so far, we've been dealing with a quantity Cn, or Cn of y in the lecture, which was a number of self-avoiding walks from 0 to y. I'm going to change this. I'm going to use the same symbol, but I'm going to change the normalization of this quantity a little bit. So I'm going to take this to be the expectation. If I don't put an index, it started at 0, or any point in the torus or ZD, of e to the minus GIN. So IN is same as I0N. The indicator function that at xn, the walk is at y. And G is a positive parameter. So how does this differ from the notation used in the lecture? Let's suppose let's first suppose the first term, the interaction term, is not present. Then we're just looking at the expectation that a simple random walk started at 0 ends at y. This is the same as the number of simple random walks started at 0 up to y up to a constant 2d to the n. So we've basically normalized with respect to the number of simple random walks. And as before, Cn will be the sum of Cny over all y. So these are weights for weakly self-avoiding walks started at 0, ending at y with n steps, and these are weights for weakly self-avoiding walks started at 0, ending anywhere, and taking n steps. So maybe I don't have to write this down. So as before, this sequence Cn is a sub-multiplicative sequence. So let me write this down. So Cn is sub. Yes. So that's right. We used to penalize by a factor z to the n, where z was 1 plus lambda.
So g is log of 1 over 1 minus lambda.
So yes. Yes. So g will take values from 0 to infinity. Lambda used to take values from 0 to 1. So it's kind of, yeah, it's the log of that, essentially. So the n square root converges, and this was called mu in the lecture. I'm also going to introduce a new notation for this, which I'm going to call e to the kappa critical. And a remark, kappa c is less than 0. Why is that? This is because we are normalizing with respect to simple random walk. There's less, the weight for, so if you think about strictly self-avoiding walk, there are fewer strictly self-avoiding walks with n steps. So the quotient of the number of strictly self-avoiding walks with respect to the number of simple random walks will be less than 1. This is the same is true for weakly self-avoiding walks. So this quotient will be less than 1, and so the number in the exponent will be negative. Also looked at the susceptibility chi of z, which was defined as a sum over all n Cn times e to the minus kappa n. So this, let me remind you, before this used to be a z to the n, which is now has now become e to the minus kappa n. And let me use this notation for oh, I'm sorry. Kappa. So what I should have said here is that these numbers depend on the graph. So these numbers will be different for the torus and for the whole hypercubic lattice. So I'm going to use the letter chi for the graph ZD, and use the quantity chi with a superscript L of kappa for the analogous quantity Cn, and maybe I should denote that now we're on the torus, I'm going to write Cn of the graph, e to the minus kappa n for gamma at torus side length L. And so what we can see immediately is that chi L, so the susceptibility on the torus of kappa, is always less or equal than the susceptibility on the whole lattice. And in particular, the critical point will be the critical value of kappa on ZD will be greater or equal than its corresponding value on the torus. I'll make a few remarks about this since. So maybe first let me give the proof, which is just a picture. Maybe I can fit it in here. Yeah. Is this big enough? So think of the torus as embedded into the plane. I need a second color. Think of the torus as embedded in the plane. Then every walk in the plane, it should write it like this, can be mapped to a corresponding walk on the torus. We're just identifying the sides. So this point will be identified with that side. So this walk will be continuing like this, exiting the torus here, and then kind of going on here. So every walk in the plane corresponds to a walk on the torus. And if we take, say, L bigger than 2, the converse will be true as well. If we're given a walk on the torus, kind of by continuity kind of argument, we'll be able to associate a unique walk on the plane. So walk X on ZD has a one-to-one correspondence to, call this a folded walk X prime on the torus. So, but in particular, from this we see that on the torus, walks can only have more intersections than on the whole plane, because this walk doesn't have any self-intersections. But suppose it went like this, then corresponding walk on the torus would go like this, and in particular, it would intersect itself at this point. So the number of self-intersections of X is less than the number of self-intersections of the folded walk X prime. And in particular, it follows that these expectations, because there's a minus in the exponent, satisfy the opposite inequality. So maybe I should put an L here for the expectation on the torus. And so this is Cn of TDL, and this is Cn of ZD. So from this, we obtain, by summing over all n, we obtain that inequality. And the second statement follows immediately, since chi L is less than chi. So if, so in particular, if chi is finite for chi C, then then it will also be finite for all values less than. Okay, maybe let me draw a picture. So actually, I don't really want a picture since it's only a one-dimensional. So maybe let me remark here that the subcritical regime corresponds to the values of chi, which are larger than the values of kappa that are larger than kappa c. Do we still have this here? Yes, because we've kind of changed we've gone to an exponential here. So in particular, if we're looking at the larger value of kappa, the susceptibility can only be smaller since it's damped more. So and since this quantity is smaller than that, it follows that the critical value where it ceases to be finite when you come from above has to be smaller than for the complete hypercubic lattice. So next, I'd like to recall what the two-point function is, and it happens to be written down here already. So this is the if D is a subset of vertices, the two-point function in this domain D is and with this parameter kappa is the function g kappa d of x and y, sum over all n of walks started at x, ending at y, staying inside the domain D for the whole time, and weighted with this weight, which accounts for the penalty of self intersections. So you can think of it in two ways, if you like. One way is it's a generating function for this sequence of numbers as a parameter of kappa, or as a function of e to the minus kappa. Or if you want, you can also think of kappa as the energy required to go to path of one unit of length more, and you're looking at the path of all possible lengths, and then this is kind of the grand canonical ensemble for paths with variable lengths, and the two-point function will be the probability that a walk started at x ends at y in the grand canonical ensemble with the chemical potential kappa. But you don't really need to use this interpretation. Anyway, this is what it is. So the Simon-Leap inequality, which was already featured in the title of this tutorial, is the following inequality for the two-point function. So g kappa, if I omit the domain, it always means I'm looking at the whole domain. So g kappa of x and y minus g kappa d of x and y is less than the sum of all z in the boundary of D. So this is domain D, and the boundary will be I'm looking at the external boundary here. That's all vertices that have neighbors in D. This is D. of walks that remain inside the closure of D, which is D union boundary of D, walks going from x to z, and the two-point function g kappa, there's no domain here from z to y. Let me illustrate what this means in a couple of examples. So first of all, so maybe let me make a second picture here so I can draw two examples. So first of all, the left-hand side counts all the walks which exit the domain D at some point, because I'm looking at the sum of all walks and subtract all walks that just stay in D. So this only counts walks which exit the domain at some point. So suppose I'm looking at a point x here and say a point y, which is in the same domain. The left-hand side will just be 0, and the content of this inequality will be trivial. Okay, yes, this is what I mean. You're right. I was going to say that the contribution of walks that just stay inside this domain will be 0. But what you can have is walks exiting the domain and come back to y. So let me write this in red. This will not count, but this does count. So these walks that just staying inside here do not count to this contribution, while there's only such walks. And then there's a point where this walk from x to y exits the domain D. So it steps to a point z on the boundary of D. And so the statement of this inequality is that you can estimate the two-point function from x to y by taking the two-point function of walks which are restricted to stay in D up to the point where it first exits the domain D, and then use a two-point function from z to y. The second example, where x is inside the domain and y is outside the domain. In this case, every walk from x to y will necessarily have to pass through the boundary. So this is so g kappa d of x and y is just the same as g kappa of x and y. And there's no walks which just stay inside D. This is 0, and the complement is. So maybe let me write this as so. This is true. This is 0. There are no walks which stay inside D. Maybe as a short historical remark, an analogous inequality has first been proven by Barry Simon and Elliott Leap for the Ising model. That's where the name Simon-Leap inequality comes from, and it basically looks analogous. I think Simon proved it without the restriction to the domain D here. It was called Simon inequality, and the same. Well, one paper after it was improved by Leap to account for this, and that's why it's called the Leap-Simon inequality. Sorry? You do assume that x is in the domain? Yes, in this picture, yes, x is in here. So let me quickly go through the proof, which is very simple. So as I said, the left-hand side is just the contribution of all walks which exit the domain D at some point. So it's e to the this expectation so I've replaced the, well, this is just what you get if you invert the opposite inequality. And looking at this expectation, we can condition on the value x assumes at td and also on the values td takes itself. So just doing that, we obtain that this is the same as sum over all z and the boundary of d, sum over all m from 0 to n, So essentially, this argument is a kind of a sub-additivity. The flavor of the argument is kind of a sub-additivity flavor. This, as in the proof of the sub-additivity of the sequence Cn, this this quantity e to the minus gin, which is, let me recall, in is the number of self-intersections the walk takes from 0 to n, is bounded above by e to the minus gim times e to the minus gimn, which is, this is the number of intersections from time m to n, and this is the number of intersections from time 0 to m. Together, they are certainly less than the number of self-intersections the walk can take from 0 to n, and we obtain this inequality. And then the rest is basically an application of the Markov property for the simple random walk. So you should not waste too much space. So this is less or equal than Ex times and this line, we can see that the quantity, that the indicator that td, the exit time of the set d is equal to m, can be replaced by td is greater than m, since we know that at time m, we're already outside the set. So in plugging this in, we basically get the inequality. With a little more work, the same argument essentially can be done for the continuous time weakly self-voiding walk. Well, it essentially works the same. Oh, no, it was there. Sorry. I was looking at the wrong line. So. So and as you can see, this quantity is basically the 2-point function, except that the strict equality sign has become a less or equal. So we replace the set D with its closure, which also includes the boundary. And in this case, we have the 2-point function on the whole graph. It is a fairly simple inequality, but even though, maybe let me just emphasize this, even though it's simple, it has a kind of remarkable consequence. As soon as we know that, for example, the sum over the 2-point function is finite, it must decay exponentially, and that's the next problem. So say if we knew that it decayed like a 1 over x with a power that's sufficiently high, so like if we had a power law decay, this would improve this to an exponential decay immediately. So how can we see this? Suppose we're given 2 points x and y, and looking at some path which goes from x to y, and we fix some integer L, and we're looking at a box of size L. Then we could cover the path from x to y by such boxes. So this path hits the box at this point. We put another box here. We hit it here. So we just go on like this. And cover the path with boxes. And the least number of boxes we're going to need to do this is if the path is a straight line. In this case, we just have to have boxes which are kind of overlapping like this to go to y. And so if I define M to be infinity norm of y divided by L plus 1, take the floor of this, we're going to need at least M boxes for every path from x to y to cover. Yes, I will take x to be 0. So yes. So let's say x is 0. But everything is translation and variant on the graphs we're looking at. So then if we just iterate this bound, we get the exponential decay immediately. So g kappa xy is less or equal than the sum, just applying the inequality. And I'm actually forgetting about the domain here. And I'm also forgetting about the domain here. And this I can do because I'm looking at this situation where the left-hand side is actually the same as just the 2-point function itself. And I can do this m times, as I explained here. So this is the first step. And while iterating this, we get m such sums. And m such factors of g with the final factor g z m to y. And okay, there's some space here. And now I'd like to, so z is in the box, say, from x and x plus the boundary of a box I call lambda. We have the same here, so x is in the boundary of the box lambda, and this is z is z1, and z2 will be in the boundary of a box around about z1, and so on. And since for kappa greater than kappa c, by definition, g kappa of 0 y summed over y is finite. We can make it less than 1 if we just sum over the boundary of a box that's big enough. So if so every one of these m factors will give every sum. So there's m sums, m factors here. They will each give a factor like this, which I'll call theta. And then there's this remaining factor, which we're just bound by its supremum, which is also finite. So okay, need a little space here. So this is less than theta to the m, the infinity norm of g kappa. And so this gives the exponential decay. And finally, as an application of this, I'd like to come back to the original problem that we'd like to approximate the two-point function on the whole lattice by a two-point function on tori, which are sufficiently large. So the fifth part of the exercise sheet, let me denote by g kappa xy the two-point function on zd, and by g kappa l xy the two-point function on a torus. And I'm going to assume that all of these tori I'm looking at, indexed by L, are embedded in ZD and are also nested. So I want to look at, so this is a torus of size L with sides identified. And so I want the torus which has a bigger size to, well, I guess I'd have, let me just say these are on a torus I call TL. So I want all of these tori to have vertex sets which are embedded or nested in each other. And this is just for convenience so that we can identify points in both graphs. So the statement is that then g kappa L xy converges as L goes to infinity to g kappa xy for subcritical kappa, that's kappa greater than kappa c. And it follows immediately by the monotone convergence theorem that the limit as kappa goes down to kappa c, followed by, well, preceding the limit as L goes to infinity, is equal to the critical 2-point function on the whole lattice. This is just because these quantities are monotone and kappa. We can take the limit. So this is the statement that we can use to make use of the finite volume subcritical renormalization group result. And it's a fairly immediate consequence of the Simon-Leap inequality. Let me first remark that so G kappa xy, this is the infinite volume 2-point function, is the limit as L goes to infinity. I'm going to say what dl is in just a second. So if I take any sequence of domains inside the whole graph that increases to the whole graph, we can just take the limit of the 2-point functions restricted to this domain by monotone convergence, since the 2-point function just sums over all walks, and they're going to be less if we restrict to a domain. So this will be increasing as this domain dl is increasing in L, and so this is just by monotone convergence. And I'd like to take dl. So let's say I'm looking at a torus with vertices lambda L. And I'd like to take dl a set which is at least two steps away from the boundary of this torus lambda L. So say dl could be lambda L minus 2 if I chose this torus so that this distance is L. So.
But in DL, you don't identify the boxes.
I don't identify the boxes. These are just sets. I identify the vertices of a torus with a set and ZD, and I'm looking at a set DL which is inside the torus, and I'm going to choose it so that both are going to infinity, but there's always some space left. So it suffices to show that the difference between this the 2-point function on the torus and the 2-point function on the whole graph restricted to the set dl is goes to 0 as L goes to infinity. And note that this quantity is actually the same as the 2-point function on the torus restricted to the same domain dl. This is just because in here I don't see the boundary, so the possible steps all of the walks inside here can take don't notice that the boundaries are identified, so it's just the same. So this we can do. And this side looks exactly like the left-hand side of the Simon-Leap inequality, which is still up on the board on the left. So this whole thing, it's enough time I can write it down again. So it's less or equal than the sum over all points in the boundary of dl So what are these two-point functions? Let's look at this one first. Well, no, let me just do one more step. So this is less than if we pull out this factor, the supremum. We can pull out the supremum of this factor in front of the sum so that we obtain sup over z in the boundary of dl g kappa dl bar l x z times the sum over the second factor. So this two-point function on the torus is still the same as the two-point function on the whole graph, since even after having taken the closure of dl, we're still not touching the boundary of the vertex set of the torus. So I can remove the L. And so we are also only making it bigger by removing the constraint that we're staying inside the set dl. But we have seen that g kappa decays exponentially in the subcritical kappa, and we are taking the supremum over a box which increases. So this will go to 0 as L goes to infinity. So all we have to see is that the second factor is finite. But that's the case, so we are summing over the boundary of dl here, which is clearly less than the sum over the whole graph, which is a torus in this case. So and that was the susceptibility as we defined it before. But we saw at the beginning of the tutorial that the susceptibility on the torus is bounded by the susceptibility on ZD. And the susceptibility on ZD is the kappa. Sorry. The susceptibility on ZD is finite by definition of the critical parameter. So this is it. I think this is all we wanted to do. If there are some questions about this or about today's lecture. No, it's the same. So yes, we're basically taking the exponential growth rate of the simple random walk out of our definition of e to the minus or e to the kappa.
For the weakly self-avoiding walk, it wasn't an integer because there were all of those factors 1 minus lambda. And now factors of e to the minus g. The only difference is that this expectation has been normalized. So what used to be z is now e to the minus kappa divided by 2d. Because there's a 1 over 2d to the end. That's that expectation. But nothing in it.
Oh, this works for. It's just the self-avoiding walk is in this case for a discrete time case. It's just the parameter g to infinity. So